Alright, so since we have the section properties calculated, now we're ready to apply the bending formula and determine the normal stresses. And in particular, we want to determine the maximum normal tensile stress and the maximum normal compressive stress. And because we have a negative moment, that implies that our moment goes like this, where 6 kilonewton millimeters is applied here, so that we have compression at the bottom and tension at the top over here. Okay, and so and our maximum normal stresses are going to occur the furthest distances away from the neutral axis, which is right at the centroid here. So I will label this line right here as the neutral axis location. So let's go ahead and calculate this sigma, the normal stresses at the top and bottom. Oh, but before, we also have to remember is that this y in the equation, this bending formula, the way that it's presented here, is saying that this positive y direction is oriented upwards here. Okay, and so at the top, when I want to calculate the the normal stress at the top of my section, so sigma top right here, I have this formula. I have minus m max times y top over I. Okay, and the reason that this y top is positive is because it's up here and it's from the neutral axis. That's a positive distance, and this would be when we substitute some numbers, this would be minus 6 kilonewton meters times the distance to the top, which would be 50 millimeters, divided by this I, the moment of inertia, 1.36 times 10 to the 6 millimeters to the fourth right here, and I want to convert into millimeters, so 1,000 millimeters per meter, and bam, this number is 2.2206 kilonewton per millimeter squared, which is the same thing as 0.2206 gigapascals, or 220.6 megapascals. Okay, and this also, by the way, is also newtons per millimeter squared, in case you needed a refresher on units. So it's really convenient to keep things in kilonewtons and millimeters and newtons and millimeters right here. And so you can see, and the positive stress result indicates that this top location is indeed in tension right here. And then we can go ahead and calculate the bottom right here. And the bottom has right here, because this is a linear relationship, all the numbers are the same except for the location right here. So it's really minus m max over I times negative yb, all right, or the distance from the neutral axis to the bottom, which is 30 millimeters, and this is going to be minus 6 kilonewton meters times 30 millimeters times the unit conversion, divided by 1.36 times 10 to the 6 millimeters to the fourth. And this number here, if you calculate the stress, is going to be negative 0.1324 kilonewtons per millimeter squared. And using the same stuff that I just showed you previously, this would be negative 132.4 megapascals right here. Now that we know what the stresses are at the top and bottom, and we are ready to draw the stress profile, which we'll do next. Now we want to draw that stress profile, and so here I've gone ahead and redrawn the section for you, and the locations to label are probably the neutral axis location, which is right about here, and that location is, I'll draw a straight line right here, and this distance was 30 millimeters, is the neutral axis location. And to draw the stress profile, I want to draw lines, horizontal lines, from the tops and bottoms of my cross section here, and then this will represent the face of my cross section. So if I took this T shape and I turned it 90 degrees out towards you, if you will, and so my neutral axis line is just going to extend that out right here. This will be my neutral axis, and it's important to note where the neutral axis, because that's the point of zero strain and therefore zero stress. And the very top of my cross section experiences a tensile stress of 220.6 megapascal. So I'll draw that over here. That point is 220.6 MPa. And so I have a stress here of 220.6 MPa, and it's linear from the zero stress at the neutral axis like this. So I have here this linear stress, tensile stress pulling here, and then at the very bottom I have negative 132.4 in compression, which means I have right about here, this is 132.4 megapascals in compression. So I am compressing the surface, if you will. And this line, oh, that was dirty right here. Oh, it's even dirtier. Okay, so here's my new 132.4, and let me clean this up a little bit. That one right there, yay. Okay, and so here my compressive stress here is 132.4. Bam, bam. And really these two lines should have the same slope, so that I should be able to continue this like this right here, and it should look exactly the same. And this is 132.4 megapascal. This is my stress profile. Now the stress profile is not a 2D thing. This thing is actually, this whole thing is extruded over the surface of the cross section here. So I would have this portion of my area would have this trianguloid-ish kind of deal, and then this portion of my cross section would be in compression, would have a T-shaped trianguloid, I guess is the way to describe it. So here's my stress profile that we finished up already, and now what's left for me to do is calculate the compression, the force resultant in the flange, and it's going to be a compression force because I have compressive stress. Because this stress is actually applied over the entire area, it's like calculating the volume of the stress block over the flange region right here, which I will highlight in orange. And so if I could draw this in 3D, what you really have is, if this is my flange area, bam, like this here, and straight, yes, right here, and my stress over that flange area is this trapezoidal volume looking thing, line figure. There would be this trapezoidal stress volume, acting on the flange zone, and what we want, the force resultant, is the volume of this stress. So Fr, from a calculus perspective, Fr is just stress dA, the stress function over the area here. But it doesn't have to be that complicated. It's really just, if I could label this point sigma 1 and this point is sigma 2, which we know is 132.4 megapascals, it's really the area of a trapezoid extruded over the width of the flange, which in this case is 60 millimeters. This depth is 20 millimeters. So this calculation is pretty simple. You don't need to do an integral. It's just Fr is this cross-sectional area, which is 1/2 the average of the sides, if you will, sigma 1 plus sigma 2, which are, in this case, are stresses, times the width of this 20 millimeters, and then times 60 millimeters. The only thing left is to calculate sigma 1, and sigma 1 is really right here at the 20 millimeter location right here. This distance is 20 millimeters from here. So this is 20 millimeters, and this should have been, this is really sigma 1. And the way that we can calculate this location is by similar triangles. And this location, if the neutral axis depth is 30 millimeters, this is 10 millimeters. And so by similar triangles, you could just say sigma 1 over 10 millimeters is equal to 132.4 megapascals over 30 millimeters, which makes sigma 1 just 1/3 of 132.4 megapascals. And that is, if you plug that into a calculator, I think it's 44.13 megapascals. And so now to calculate the force resultant, it's just 1/2 44.13 plus 132.4 megapascals, which is newtons per millimeter squared. Yes, and 20 millimeters times 60 millimeters. And when you work out some numbers and substitute, this whole deal becomes 105,918 newtons, which is really better expressed in kilonewtons, 105.9 kilonewtons here. And that is my compressive force resultant. So if I could, it'd be a squiggly line here. This would be FR. Bam! Alright, so hopefully that has been useful and it helps you see the application of the bending formula and all that's involved. If you have any questions, let me know. See ya.